Chapter 5, chemical reactions. We've looked at chemical reactions a little bit. Chemical equations, chemical reactions occur all around us. A chemical equation is just a way that we represent something happening. So a chemical equation just describes some chemical process. We're describing what's going on with the chemicals. We can't really see like exactly what's going on at the chemical level, but a lot of times we can figure out, what's going on. We can figure out we started with these things, we know we started with these things, and we got to these things in the end. Generally, it's just like describing a process. So it's sort of like describing a football play, dropping your phone. It's like food recipes. We're just describing something. So in the case of like dropping a phone, the reactants of that dropping a phone, I have a phone. I dropped the phone and it hit a rock. So the reactants for dropping a phone plus rock. The products, you might be able to guess. Broken phone. And guess what? Still got the rock. That would be sort of like an example. Our chemical equations in this class are very simple. It's just what did we have before things happened, and what did we have after things happened. If you want more exhaustive descriptions of chemical reactions, organic chemistry, where you'll encounter some of that, where you'll not only have here's the reactants and here's the products, but you'll also be asked, how did we get there? What was the journey? What was the process? Or they'll say, here's where you're starting, here's where you're ending. Tell me how to get there. Tell me how to get from this chemical to the other chemical and what chemicals are in between. We don't do that in this class, but if you want to do that, organic chemistry. Or maybe that's something you can look forward to. Oh, look at that. So the drop my phone hit a rock, now my screen's cracked. Phone screen plus rock, cracked screen, the rock is still there. Another example of a word version of a chemical equation. Methane gas reacts with oxygen to form carbon dioxide and water. So methane plus oxygen. Methane gas reacts with oxygen. So we're linking those together. And then we've got a signal word, to form. That's basically standing in for our arrow. And then everything else after this is our products. Sort of the breakdown there. Chemical equations are what we use to represent chemical reactions. It saves us some time and space. The substances on the left side, as a reminder, are reactants. So we've got our reactants. This is actually that same equation that we described earlier. Reactants. And on the right side are the products. We often indicate the physical state, the phase of matter, the state of matter that it is. In this case, these are all gases. So a G for gas. So what we have before the reaction occurs on the left side, what we have after the reaction occurs on the right side. We can get a skeleton equation or a skeletal equation. What's a skeleton? Bones, bare bones, nothing on top of it, right? So this is our bare bones equation. Just the basics. So our skeletal equation is our bare bones equation. A lot of the other information's been stripped away. It shows only the formulas. Got the formulas for the reactants and the products. In this case, we've substituted in chemical formulas for the chemical names. Typically, like 99% of the time, we use formulas instead of names. The only reason that we've been using names previously, we didn't have the nomenclature, and also it's maybe a little bit easier for you to parse, for you to understand, for your brain to comprehend with words there instead of chemical formulas. So we're going to be seeing chemical formulas a lot more now instead of names. So this is a skeleton equation. Here's a little key. Some of the symbols that are used. We've got the plus. That just means we're separating multiple reactants or products. We've got our arrow, reactants and products. We can also have a double-headed arrow, meaning that it goes forward and backwards. Reaction goes both ways. We'll see those later, or more later. And then we've got each of our state signs. So we've got S for solid, L for liquid, G for gas, AQ for aqueous, which means that it's dissolved in water. If we look at our skeleton equation, our bare bones skeletal equation, this is the same reaction that we were looking at before. We've got a problem. The problem, one of the problems at least, is that on our reactant side we've got two oxygen atoms in our O2. Does anyone know why it's O2? This is just how oxygen normally exists. Why? How would we know that? Horses. Horses what? Who remembers what horses? Horses need oats for clear brown eyes. Oats starts with an O. Oxygen starts with an O. Oxygen is one of our diatomic or molecular elements. That's why oxygen would be like that. So we've got two oxygen atoms. On the reactant side, we have three oxygen atoms on the right side. We've got two oxygens in CO2, and we've got one in H2O. So somehow, the way that we've got this written out, we've got two oxygen atoms on the left side and three on the right side. We know the law of conservation of matter, right? Matter must be conserved. We cannot simply have three oxygen atoms on the right side and only two on the left side. We have to have the same number on both sides. We also have a problem with our hydrogen. We've got four hydrogen atoms on the left side and two hydrogen atoms on the right side. This is not allowed. This is illegal. We need to have balanced numbers of each of our elements on both sides. So we need a balanced equation. A balanced equation has the same number of every element, same number of an element, let's say, but for each of them on both sides. Matter is conserved in a balanced chemical equation. In order to balance an equation, we can insert coefficients. So we've got some coefficients. We can add coefficients in front. So these 2 means that we've got two O2s. This 2 means that we've got two H2Os. We're not going to change the subscripts, the little 2's that follow the letters, or the little 4. All right, we're not going to change any of those because if we change those, it's a different chemical. So we're using the same chemicals, but we can change the ratio, the amount that we add. This would be like if your friend gave you a recipe for pancakes, and they just told you you add cups of flour with eggs with water, and you just like throw like 1 cup of flour and 1 egg and then like 1 cup of water and you mix it together and you're like, this is a pancake mix, and then you try making it and it's awful, right? We can adjust the amount of the ingredients. We might have more flour, more egg, a little less water. We're not going to swap out the water for vinegar for our pancakes. We're not going to swap out the flour for like corn syrup or tapioca or gelatin, right? We're going to use the same ingredients. We're just going to change the amounts of the ingredients. So we can change the amount of the ingredients. We're not going to change the actual ingredients themselves. Ingredients here being our chemicals. We've got steps. There's some steps for doing this. So the first thing that we want to do, if we weren't given the reactants and the products, is we need the chemical formulas for each of the reactants and products. This might require us to use our nomenclature knowledge. So we might be given words instead of formulas. So we have to turn words or names into formulas. And then we can write out the skeletal equation. We can put the things that react, the reactants, on the left. Put the products on the right. Just getting everything in place where it's supposed to go. Then, if an element, because we're going to be balancing this based on elements, if an element occurs in only one compound on both sides, we can balance that first. Part of the reason for this is we're going to be changing something. It's going to be in a compound. So that means when we change it, when we change those coefficients, it's also going to change one of our other chemicals at the same time. So we want to get out the big changes out of the way first. If we have more than one element like that, the rule here, balance metals before nonmetals. So if it's in one thing on both sides, we're going to balance it. If we have an element that occurs as a free element, like H2 or O2 or N2, if it's just that one element by itself, it's not in a compound, then we want to balance those last. The reason that we want to balance those last is because we can change that number up or down as much as we want. It's not going to change anything else. So it's not going to affect our other elements. So that means that it's really easy to balance that one thing, that last thing. And then this number 5 that we won't encounter much, but there are occasions where we will encounter it. If we have coefficient fractions, so if you've got a 1/2 or a 9/2 or a 4.5, which is the same as 9/2, we can change those by multiplying the whole equation by the appropriate factor. For all of these, we'd be multiplying by 2 to get rid of those. The reason that we would run into these coefficient fractions is if we have one of these free elements. It might be that we need, like for O2, we might need to add not 2 more oxygens, but 1 more oxygen, so we'd have to use a fraction to get our oxygens to match. That's actually faster than going and rebalancing everything so that we don't have to do the fraction. I think we have an example of that. Do we have any questions before we jump into practical examples? Any questions about the rules? Cool. Oh, just kidding, there's one more rule. Check and make sure that everything is balanced. I often skip this step because of my hubris. also called confidence or arrogance. Okay, so we can also double check things. We'll probably do that a couple of times. In summary, some things that we want to talk about. Do change the coefficients. Number in front of a chemical. Wow, look at that. I have it written right below it. Number in front of a chemical, like 2CH4. The 2 would be a coefficient. Do not change the subscripts, like the 4 in the CH4. If you change the 4 in CH4, it becomes a different chemical. And our overall goal is we have the same number of atoms of each element, same number of carbons on the left and the right, same number of oxygens on the left and the right, same number of hydrogens on the left and the right, whatever elements we have. So an example. Write a balanced equation for the combustion reaction of gaseous C2H6 and gaseous oxygen to form gaseous carbon dioxide and gaseous water. Our first steps, we need the chemical names, or the chemical formulas for these names. One of them we're given, C2H6. That's because we don't know the nomenclature for naming that. So C2H6, its state is gas. So put a little G in parentheses behind it. This is the reaction of gaseous C2H6 and gaseous oxygen. What are we going to write for oxygen? How does oxygen normally exist? Is it O? Is it O4? Is it O3? Is it O2? Is it O, shoot, I forgot? It's O2. So plus O2, possibly also from our Fonkel brick ship. Just kidding, it's not Fonkel brick ship, that's a different one. Brinkelhoff. Getting my mnemonics twisted. And then the problem says to form. To form signals are arrow, reaction arrow. So now everything that follows that is our products. We've got gaseous carbon dioxide. What's special about the name carbon dioxide? What might signal us in as to what kind of chemical this is? Dioxide. It's got a prefix in it. We only use prefixes for molecular compounds. We can also see that it's carbon and oxygen because of the oxide. So it's a molecular compound. So we've got 2 oxygens. How many carbons do we have? 1. We omit the mono if it's the first thing. So carbon dioxide is CO2. This is also a gas. And gaseous water, which is H2O. So that's our skeleton equation, or our skeletal equation. Now we need to balance. So our rule is that we want to balance things that occur in only one compound on both sides first. So things that occur in only one compound on both sides, we've got carbon. Carbon is in C2H6. Carbon is also in CO2. Hydrogen is in C2H6. Hydrogen is also in H2O. They're only in one thing on both sides. We can start with either of them. I'm going to choose to start with carbon because it shows up first. The way that I do my balancing for chemical equations is I'll write down the element underneath the arrow. We can write out how many we have on the left. We can write out how many we have on the right. So currently, on the left side, on the reactant side, we have 2 carbons. On the product side, we have 1 carbon. We want those numbers to be equal. The way that we can get them to be equal if we put a coefficient of 2 in front of CO2, now we've got 2 carbons. The other thing that was in one thing on both sides, one compound on both sides, was our hydrogens. So we can balance hydrogen next. We've got 6 hydrogens on the left side because of the coefficient. We've got 2 hydrogens on the right side because of the coefficient of 2 in H2O. To get those numbers to be equal, what do we have to do? We want to get this 2 to be a 6. What do we multiply 2 by to get 6? 3. So we're going to put a coefficient of 3. If we put 3 in front of our H2O, we've got 3 times 2 hydrogens for 6, so our hydrogens are balanced. Then we can balance our oxygen. We balance our oxygen last because oxygen is by itself on the left side. That means that when we change the coefficient in front of this oxygen, it doesn't affect our carbon or our hydrogen. So we don't have to go back and rebalance carbon and hydrogen. So our oxygen, currently we've got 2 on the left side because of the subscript of 2 on O2. On the right side, we've got 2 times 2 for 4, plus 3 times 1 for 3. So we've got 4 plus 3, that's 7 oxygens. What do we need to multiply 2 by to get 7? We're trying to figure out what we need to put in front of our O2. 2 times what is 7? Or 7 divided by 2 is what? 3.5. We have to multiply it by 3.5. So we can put a coefficient of 3.5 in front here. Or we could put in the fraction form 7 over 2. That would also work. I like 7 over 2 because it shows us what we need to multiply by. Right, the number that's in the bottom, we multiply by that, and it turns into 7. 3.5 also works. Do either of them. Okay, so we've got everything balanced. We've got 2 carbons on the left side and the right side, 6 hydrogens on the left side and the right side, 7 oxygens on the left side and the right side. Can we have half of an O2 molecule? No, because then it wouldn't be an O2 molecule, right? Like we can't have half of a student in the classroom, because that wouldn't be a student, that would be a crime scene. So we need to get rid of those fractional coefficients, the non-whole number coefficients. This is where that multiplying part comes in. So we're going to multiply everything by 2. So we would get 2 C2H6 gaseous plus 7 O2 goes to 4 CO2, also gas, plus 6 H2O, also gas. And then the last step would be to just check and make sure that we did everything correctly. It's not uncommon that you do this times 2 and you just forget to do it to one of these coefficients. So we're going to run through real quick and check. So for our carbons, we've got a subscript of 2, coefficient of 2, we've got 4 carbons. On the right side, we've got 4 carbons. Carbons are balanced. Hydrogens, we've got 6 times 2 for 12. We've got 6 times 2 for 12 on the right side also. On the left side, for our oxygens, we've got 14. 7 times 2 is 14. On the right side, we've got 4 times 2 is 8, plus 6, 14. So everything's balanced. I didn't write it out because I ran out of room. That's a recurring theme for the class. Me running out of room, not me not writing stuff. Questions about any of the steps? If you really hate doing this 7/2 or this 3.5, strictly speaking, you don't have to do that. It is the easiest, fastest method. You could also go back and you could change other stuff. There's lots of different ways to arrive at the same conclusion. This, I think, is the fastest and simplest. All right, here's an example of a different type of chemical equation. So the one that we were looking at before, we had instances where we had one thing only on both sides. This is a different type of balancing situation, and I'm going to show you how I like balancing these ones. First step, we need our skeleton equation. We need to turn names into letters and numbers. We are told aqueous solutions of lead 2 nitrate and sodium chloride are mixed. Are mixed meaning there's something of a reaction. We're even told that the products are aqueous solutions of sodium nitrate and solid precipitate lead 2 chloride. So our first sentence tells us our reactants. We've got lead 2 nitrate. Lead is Pb. What is nitrate? Sorry, it's also lead 2, so lead 2 plus. What's nitrate? Refer to your green sheet. NO3 with what charge? Negative. NO3 minus. This is an ionic compound. We need to crisscross these. So this will be Pb parentheses NO3 close parentheses 2, and it's AQ. First chemical. Second chemical, sodium chloride. Sodium is Na, chlorine, the base for chloride, is Cl. What charge does sodium form when it's an ion? Find it on the periodic table.
1+.
Yeah, it's a 1 plus. Sodium plus. How about Cl? All the way on the right side, 1 over. It's 1 spot over from our noble gases. It's going to form Cl minus. We can combine these 1 to 1. So we've got ourselves some good old NaCl. Okay, so PbNO32 and NaCl. Those are our reactants. Our products are aqueous sodium nitrate. We've got sodium and nitrate already. We can see sodium's 1 plus, nitrate is 1 minus. So this is going to be NaNO3, NaNO3, also aqueous. And our last one, lead 2 chloride, so Pb2 plus. NCl minus. You could crisscross those and you would get PbCl2, and this one is a solid. So that's our skeletal equation. Then our steps tell us to balance the things that are in only one compound on both sides. So let's track down what's only in one compound on both sides. Looking at lead, we've got lead in one thing on the left side and one thing on the right side. Okay? We've got NO3 in one thing on the left side and one thing on the right side. As a note, right, these polyatomic ions, these oxyanions, we clump those together as one group. We're not going to be breaking those up. So you can treat NO3 as one group. So we'll balance NO3 all at once rather than nitrogen and oxygen separately. So NO3 is in only one thing on both sides. Na is, it's in one thing on both sides. And Cl is also in one thing on both sides. So what do we start with? The answer is it doesn't really matter. The way that I like to balance these is we're going to start with anything that's different. What is one thing that's different on the left, the number of things on the left versus the things on the right? What's one that's different? Cl. So we can start with Cl. Okay, so Cl is different on the left and the right. On the left, we've got 1. On the right, we've got 2. To get these to balance out, we need a coefficient of 2 in front of our sodium chloride, our NaCl. What changes other than the Cl when we do that? What's the other thing in NaCl? The sodium, the Na. So let's balance that next. So we're going to balance the thing that we just changed. So Na, we've got now 2 on the left side. On the right side, we have how many? We've got 1. It's in this NaNO3. To get these to balance, we need a 2 in front of our NaNO3. So we'll add in a 2. Now that's balanced. When we did this balancing, what else changed? The nitrate, the NO3. So we will balance the nitrate next. Do we see what I'm doing? We're balancing something, we change something when we do that, we're going to that next. So we're kind of like following our steps, bouncing around. I think this is the easiest way to solve these ones where we don't have anything by itself. It doesn't always work. Doesn't always work, but it usually works. So NO3, we have 2 on the right side. We just changed that. And on the left side, oh, look at that, we've got 2. So this one's already balanced. And then we just need to check and make sure that our last thing is balanced. That last thing being Pb, lead. We've got 1 lead on the left side, 1 lead on the right side. So we are balanced. You don't have to do it this way, just as long as you arrive at the number of things on the left side being the same as the number of things on the right side. And the coefficients also have to be simplified. All right, here's one for you to try. Yeah, we'll say a little bit later. Here's one for you to try. Balance this chemical equation. Aqueous lead-2 sulfate, aqueous potassium iodide to form solid lead-2 iodide and aqueous potassium sulfate. Give you about 5 minutes. It was about 2 minutes. In case you're getting stuck on the nomenclature part, I'm going to write out the what these are, just so that we're not getting caught up on nomenclature. So lead-2 sulfate is PbSO4, AQ. Potassium iodide is Ki, also AQ. These form lead-2 iodide, PbI2, that's a solid, and aqueous potassium sulfate, K2SO4, AQ. So if you're having trouble getting started with the nomenclature and the names and stuff, there's our skeleton equation. Now you can balance it. All right, that was a little bit more time. For balancing this type of thing, if we go through and look, all of the chemicals show up one time on each side. So PB shows up once on the left, once on the right. SO4 shows up once on the left, once on the right. K shows up once on the left, once on the right. I shows up once on the left, once on the right. So we want to start with anything that's just simply not balanced. So we can start with either the I2, the iodine, or the potassium. So if we start with potassium, we've got 2 on the product side, 1 on the reactant side. 2 on the product, 1 on the reactant. To get those to balance out, we need a coefficient of 2 in front of our Ki. When we do that, it changes I. Now we've got 2 on the left side, and we've also got 2 on the right side. Usually when we get to something like this, that means we're done with balancing. So let's just go through and check. So our PB, 1 and 1. And our SO4, 1 and 1. Any questions about solving this one? Could include nomenclature. All right, and then next class, we'll pick up here working on balancing this chemical equation.